All right, so the sarcomeres, those are those very basic things. They have the thick filaments. This is a slightly different picture than the last time, but it's the same thing. Thick filament is here. The thin filament is here. It comes out to this Z-line, and the Z-line is what we see as the striations in a muscle. All right, and so I can put a bunch of sarcomeres that are aligned in series this way, where there's one after another, after another, after another, or I can take a sarcomere and I can add them in parallel. And so if they're aligned in parallel, so all of the sarcomeres, all of the contractile and regulatory proteins are in this parallel structure. Now we've got a bigger, basically wider sarcomere versus here where we have this longer contractile structure. And so now what we're going to do is, what we know is that if I contract these two muscles, and yes, there's only 4 sarcomeres here, and there's really probably 2 sarcomeres here, 2 sarcomeres wide, what we can say is that if we contract and we hold on to the ends on each side, the top one is going to contract really far, really fast. Okay, because if we activate all of the thick filaments and they all start doing power strokes and they all start pulling, everything's going to shorten, and you're going to shorten because you have 4 of them in series. You're going to shorten 4 times as much as one. So this one would shorten twice as much as the one below because you've shortened the same sarcomere the same amount. Each sarcomere shortens the same amount. So if I have 4 that are aligned one after the other, I'm going to decrease by a factor of 4. And in the bottom one where I have 2 aligned one after the other, now I'm only going to decrease this space by a factor of 2. And so in the same amount of time, I've contracted the top one 4, and I've contracted the bottom one 2. So really what we're saying is that if I align sarcomeres in series, I can have this muscle contract faster than if I have them aligned in parallel. But because the force that this one sarcomere or these sarcomeres are going to produce is going to be proportional to the number of these thick filaments binding to thin filaments in parallel, this bottom arrangement where I have 2 sarcomeres wide, now what this is going to do is this is going to have more sarcomeres or more contractile protein in a given area, so the bottom one is actually going to be stronger. So what we've done is we've taken the 4 different sarcomeres, we've aligned them in 2 different ways. 1 sarcomere thick but long, or 2 sarcomeres thick but shorter. The bottom one that's thicker or that's aligned in parallel, that's going to be stronger because you've got more contractile protein in that space, whereas this top arrangement is going to mean that you can contract that muscle faster. Beyond the arrangement of the sarcomeres, if I open the sarcomeres or close the sarcomeres a little bit more or less, I'm going to be able to produce more or less force, because you can see here that some of the thick filaments, the myosin isn't touching an actin. So it's not at its ideal length, because if I was at my strongest position, each of the little myosin arms would be grabbing onto the actin. And this is what we call the length tension relationship. So what we can see is this is where we start. We start with our little gloves hanging out. The myosins are up there. They can all touch an actin. And so now they're all in a really good position to grab onto actin and pull. And they're all going to be pulling at different times. So because each myosin can find an actin molecule and bind to it, now this is the optimal resting length. Because now this is going to allow all of the myosins and all of the actins to be able to touch each other. When we extend a little bit, so we stretch a little bit further, and we stretch our sarcomeres a little bit more open, what you can see is there's a few myosin heads that can't bind to actin, and as a result, the force that this muscle, this sarcomere can produce is going to decrease. And as we pull it further and further and further, we're eventually going to get to the point where there's no myosin and actin overlapping, and you're not going to produce any tension or any force. And so what we can see down below is this is the optimum length. It's around 2.1 microns. So it's really, really small. It's really, really small. And if I pull it to 2.6 microns, I'm already losing force quite significantly. I'm down 20% of my force. If I go the other way and I start shortening, what's going to happen is the thin filaments are going to start to touch each other. And you can see that here. And then there's going to be a little bit of resistance. So if I want to keep pulling, but there's something that's pushing against me, I am going to not be able to produce the same amount of net force, even though I've got myosin and actin overlapping here. All right, so what I'm going to find is that once the thin filaments start to touch, now what I'm going to have is I'm going to have, about a 20% decrease in the tension or the force that this sarcomere can produce. And if I continue to contract it, what will happen is eventually the myosin, or the thin filaments, I should say, will slide a little past each other. And so they'll just kind of arrange a little bit, and now they're not going to be pushing as much against each other. They're going to be sliding, so they're going to be producing a resistive kind of shear force as they slide past each other, until you get to the point where the myosin heads actually are at the Z line. And there's no further distance that the myosin can go. And again, at that point, now we're down to 0. So you can see what happens is you're at the good length, the thin filaments are like this. You get to this point where some of them are touching. Now we're losing. Now more of them are touching. These first ones are starting to slide past each other. Now we're getting this sliding resistance. And then what happens, the other ones touch and they start sliding until the myosin is at the end of the pocket or at the Z line, and you can't produce, no matter how much more calcium is there. The myosins just have no place to go. All right, so what we're ideally going to do is we're going to use our muscles when they're at this optimal resting length, or at this optimal length of around 2.1 to 2.2 sarcomere microns long for each sarcomere. When we extend it, now the myosins don't touch actins. When we shorten it too much, now the actins start pushing against each other in the thin filament. All right, so that's basically how we would look at it. The muscle, if I pull it a little bit longer, it's got this nice area where it's really working well. If I stretch it a little bit too much, you can't quite start the movement. And if I let it come in too much, now I can't even contract my muscle when I'm even trying to. Okay, so really there's this sweet spot where the sarcomeres have good myosin overlap, good thick and thin filament overlap. The thin filaments aren't touching, and all of the thick filaments have a contact with the thin filament. All right, so these are two different ways that we're looking at regulating the amount of tension or the amount of force that we can produce. One is how we arrange our sarcomeres. The more sarcomeres we have in parallel, the stronger our muscle. The more sarcomeres in series we have, the faster our contraction can be. And we always are trying to work around this very limited range of about 1.8 to about 2.4 micron sarcomere length. So then those are a couple of ways that we can regulate the force that a muscle produces. The other way that we can do this structurally is we can change what the muscle looks like. So there's a few types of different architectures that the muscle has. And a muscle can produce all of its fibers in one straight line. They're all aligned along the line of the muscle. You've got the tendon here as the white bit on either end. And now all of the fibers are straight up and down. And now when it contracts, it's just moving straight up and down. All right? That's one way to align your muscle fibers. Another way to align the muscle fibers is at an angle, or what we call at a pennation. So what happens is, if now we are going to take a muscle, and again, because the muscle's strength is related to its physiological cross-section, there's two ways that we can change the cross-section. We can make each individual fiber bigger, or we can take the fibers and we can change the angle so that we can fit more fibers into the muscle. And that's what I'm showing here, is that the fibers in this muscle are aligned at about a 45-degree angle. And now this muscle is functionally thicker, even though we haven't really changed the number of fibers. If I have 10 fibers going straight up and down here, and 5 fibers going out this way, and 5 fibers going down this way, same number of fibers, but now just because I've changed the orientation, now we have a pennate muscle that's thicker than a fusiform muscle. So all I've done is change the angle, and now I'm pulling at an angle, which means that I can put more individuals in the same space. Think of it as a tug of war. If I have a tug of war and we're all lined up, all of my motors, all of my myosins are lined up along one line, I can produce a good amount of force. But if you have this one line, this one rope that you're grabbing on, and then what I do on my side is I tie off little ropes into my big rope, and I have people now, instead of having one person in that space, now I can fit two people because I can have one rope going each way. And so now I can put in more people into the same space. And so when we pull, we're pulling at an angle, and we're going to be able to pull, because there's two people in the same space as one. Now we're going to pull twice as hard. Okay, so just by changing the architecture of how we've put the fibers into the muscle, we're going to change how much muscle force that muscle can produce. All right, so there's three real ways that we're changing the force of the muscle. Increasing the number of sarcomeres in parallel makes that muscle sarcomere structure, that muscle fiber, is stronger. When we're going to work within that optimal length so that we're not too stretched and we're not too contracted, that's going to be the strongest point of a muscle. And our muscles can be designed so that they have this pennate architecture. So if we need a strong muscle, we're going to have it be pennate. If we need a fast muscle, we're going to want it to be more fusiform. Again, because in the same amount of contraction, you're shortening, because all of the fibers in the same direction, you're shortening from top to bottom a lot faster than you are if you have a pennate muscle. Okay, so just by changing how the muscles arrange, we've changed the functionality.